Today, we are going to discuss the solid state chemistry part 2. In this program, in solid state part 2, I would like to discuss about the calculation of the dimensions of the unit cell. That is one topic. Second topic is close packing crystal structures. This is very complicated to study about the close packings. If you observe this video carefully, you will get clear idea about the close packings. After that, we will study about the voids present in the close packings, and after that, we have to study about the imperfections in the solids, so on and so forth. So, let us see dimensions. Generally in the crystals, the spheres are very closely packed. To study about the crystal structure, it is not possible to observe the crystal structure by using visible light. Why? Because the atom's size is nearly 2 into 10 power minus 8 centimeters. In general, atomic size is like that. The visible rays wavelength is more than this, that is 10 power minus 7 centimeters like that, whereas X-rays wavelength is little bit lesser than this dimension, that is nearly X-rays nearly 10 power 4 into 10 power minus 8 centimeters. So, visible rays is having more wavelength than X-rays. So, visible rays is not useful to locate the sphere in the crystal. That is why in the crystal structure determination, X-rays are being used. X-ray diffraction studies conducted by Bragg gives about the complicated structures of the crystals. So, let us see the Bragg's equation, how it deals with. Let us see. W.H. Bragg proposed an equation to explain the relationship between interplanar distances, that is d, interplanar distance d, and wavelength of the X-rays incident on the crystal lattice lambda, and the diffracted angle theta. That equation was n lambda is equal to 2d sin theta. How this relation came? Let us see. Consider a crystal. This is a crystal plane, this is third plane. This is layer 1, this is layer 2, layer 3. Consider an X-ray falling on this first layer. Say here one atom is present. When this X-ray, first X-ray strikes the surface of the crystal because of the atom or sphere present over here, it gets diffracted, and this is the emitted X-ray. This is the direction of emitted light. Consider the second X-ray. It is passing through the first layer and striking at another point of the second layer and diffracted in this way. Second layer, second X-ray. This is the direction of the path. Still there are some more spheres in those planes. X-ray strikes the face A and diffracted at point B. Second X-ray strikes the second layer and diffracted at point B. If you observe the path of the X-rays 1 and 2, the second X-ray has travelled more distance in the crystal from here to here, here to here. So, second X-ray has travelled more distance when compared with the first X-ray. This is extra distance here to here, extra distance travelled by second X-ray. Say point C, this is point D. From A to B, point small d. Small d is the interplanar distance in the crystal. So, from this extra distance travelled by second X-ray is known as path difference. Path difference. So, path difference is equal to BC plus here to here, BD. Let us consider in triangle ABC. In this triangle, A to B is the D, and the first ray diffracted with a diffracted angle theta. This is the sin theta, sin theta. In triangle ABC, sin theta is equal to BC by AB, which is nothing but BC by AB is nothing but D. Therefore, BC is equal to D sin theta. Let us assume in triangle ABD, sin theta is equal to BD by AB, nothing but BD by D. Therefore, BD is equal to D sin theta. We know the path difference path difference is proportional to an integral multiple of wavelength of the X-rays. That means BC plus BD is equal to n lambda. BC is how much? D sin theta. BD is how much? D sin theta. Now add this BC plus BD, D sin theta plus D sin theta is equal to n lambda. So 2D sin theta is equal to n lambda. This is the Bragg's equation, where D is the distance between two successive planes in the crystal, theta is the angle of diffracted X-ray, n is the order of diffraction. It may be first order, second order, third order of diffractions, and the lambda is equal to the X-rays wavelength. So this particular relation gives an idea about the interplanar distances in the crystal. This will lead to study the close packings and all. So in competitive examinations like mains and NEET, generally numerical questions will be given on the Bragg's equation. Let us see one numerical question based on Bragg's equation. The objective question is, the second order diffraction of X-rays have wavelength of 1 angstrom from a set of parallel planes in a metal occurs at an angle of 30 degrees. The distance between the scattered planes in the crystal was asked. Let us solve this problem. Two parallel planes are present. First order diffraction, and this is the second order diffraction. You see, wavelength of the X-rays was given. Just by reading this question, student should think especially the topic of the question. So once you got a thought in your mind, suppose the thought is like this: after reading this question, I am able to know this belongs to Bragg's equation question. Immediately you have to recollect the question and the appropriate equation for that. So for Bragg's equation, we know n lambda is equal to 2d sin theta. This equation we have to use to solve the questions on Bragg's equation. So once you got collected this equation, then again read the problem. So what is the wavelength given in the problem? 1 angstrom unit. So lambda is 1 angstrom unit, and distance between the planes was asked, D is asked, and the theta is 30 degrees. The second order diffraction, so n was given as 2. Now find out the distance here. The distance between these two planes, find out. So distance is equal to n lambda by 2 sin theta. order of diffraction n is 2, wavelength is 1, and in the denominator 2. You know sin 30 is how much? Since the wavelength is in angstrom units, the distance is also represented in angstrom units. Now, answer is second option. So, students, let us calculate the density of the crystal. Calculation of density of unit cell. We know density of any substance is equal to its mass by volume. Density is mass of the substance by its volume. Here we are supposed to calculate the density of the unit cell like this. This is the volume. Volume is this is the edge length. This is another edge A. Volume is A cube. Here in this unit cell, the several lattice points are present. In each lattice point, the atoms or ions, whatever may be the constant particles, they are present. The total number of particles in the unit cell, first you have to calculate it first. Total number of atoms per unit cell. Z, number of atoms per unit cell. If it is primitive or simple cubic unit cell, in simple cubic unit cell only spheres are present at corners. So, 8 corners are present in a cube. Contribution of sphere in each corner is 1 by 8. So, for simple cubic Z is equal to 1. Similarly, for BCC, corners we shall take 8 into 1 by 8 and 1 at body center. So, for BCC crystal, that is how much? 2. For FCC, in FCC, 8 atoms are present at corners. Its contribution is 8 into 1 by 8. And at face centers, there are 6 faces. So, at face centers, the contribution of the atom or ion at face center is half. So, 6 faces into half. There are 12 edges in this. If it is ionic compound, the opposite charge ions will be present in the edge. If it is metallic crystal, if it is FCC, the contribution is 4. So, for FCC, Z is equal to 4. So, number of atoms per unit cell is calculated. To calculate the density of that unit cell, we have to know the mass of the each sphere. Mass of each sphere is given by its atomic weight. Atomic weight of any element depends upon its constant protons and neutrons. Here, mass of each sphere is found out by using Avogadro number. If the mass equivalent to its molar mass, it contains Avogadro number. When the molar mass is divided with Avogadro number, you will get the mass of each sphere. So, molar mass by Avogadro number gives the mass of each sphere. Therefore, density of the crystal is equal to number of atoms per unit cell into mass of each sphere by volume of the unit cell. So, D is equal to number of atoms per unit cell Z, mass of each unit cell m by Avogadro number, and volume of the unit cell is A cube. This is the formula used to calculate the density of the unit cell. Let us have a numerical questions on this density of the unit cell. The question is, at room temperature, polonium whose atomic weight is 209 crystallizes in a primitive cubic unit cell. Primitive cubic unit cell of edge length is 3.36 angstroms, and the theoretical density of the polonium is to be calculated. As I said, so this is belongs to the calculation of density of the unit cell. So, density of the unit cell is nothing but number of atoms and mass of each atom by volume of the unit cell, that is A cube. This is a formula used to calculate the density of the crystal. So, here for primitive cubic is nothing but simple cubic. For simple cubic, number of atoms per unit cell are 1. The atomic weight was given as 209 by Avogadro number into 1 by volume cube, 1 by volume cube. So, how volume cube gets? Already in this edge length was given, how much? 3.36 angstroms. 3.36 multiplied with 10 power minus 8, it becomes in centimeters. This is in grams, this is in centimeters whole cube, so centimeter cube. On simplification of this, you will get 209 by 27.1 like that. Then the density is nearly 9.2 grams per cm cube. Any crystal is considered to be present or composed of large number of hard spheres, and they are highly compactly packed in the lattice. So, their structure determination is very difficult to understand. Most of the students are also feels that the close packings topic is somewhat tricky, and it is somewhat difficult because we have to assume the 3-dimensional arrangements of atoms. Once you have an idea about the 3-dimensional arrangements, then it will be very easy to the student to catch up the subject. So, in this class I would like to explain in a simpler way, because it is very difficult topic. So, I would like to elevate in a simpler way. So, close packing generally involves in 3-dimensional packing. So, to explain the close packings, first you have to learn about the single dimensional packing. Close packing is studied in 3 stages. Packing in single dimension, packing in 2 dimensions, packing in 3 dimensions. When you talk about the packing in single dimension, this is one sphere, adjacent sphere, adjacent sphere. So, in the crystal, the simplified structure is this type of packing, sphere by sphere. So, see here, this middle sphere is in contact with 2 other spheres. So, packing in single dimensional coordination number is 2, because each sphere is in contact with 2 other spheres. So, packing in single dimension gives nothing but it is a row of atoms in a straight line, row of atoms in a straight line. When you talk about the packing in 2 dimension, 2-dimensional packing, say this is in x direction, the same type of spheres will repeat in the y direction, then we will get a layer. So, this packing in 2 dimensions is again studied in 2 ways. Square close packing, hexagonal close packing. What do you mean by square close packing? This is a sphere. This type of arrangement is single dimension. On each sphere, if another sphere is vertically aligned, alignment is taken place, vertically aligned like this, vertically aligned. This space is called void space. This space is called void space, and if you observe this, 2 spheres are in contact with 2 spheres. So, these 4 spheres are very closely present in the 2-dimensional structure. Say this is A layer, similar A layer is present over it. This is also similar layer. So, in square close packing structure, coordination number is how much? The sphere is contact with 3 other, total 4. Coordination number is 4. And it is a AAA type of packing or pattern of arrangement. Square close packing is AAA type of pattern of arrangement. This is one kind of two-dimensional close packing. If you talk about the hexagonal close packing, it is similar, but slightly difference is there in the alignment. Say this is the layer A. All spheres are in a row. Second layer is exactly aligned in the depressions of the first layer spheres. That is the difference. Here, in square close packing, layer by layer vertically arranged, whereas in the hexagonal close packing, first layer, this is say second layer B. So, in the first layer depressions, depression means this one. In the first layer depressions, second layer spheres are packed. Now, another layer will be, that means third layer will be analogous with the first layer here. So, again this is A. So, hexagonal close packing is which type? It is AB, AB, AB type. If you observe the coordination number, see 1, 2, 3, 4, 5, 6. These 6 spheres are very closely arranged in the crystal. So, coordination number of hexagonal close packing is 6. Coordination number for single dimensional close packing is 2. Square close packing is 4. Hexagonal close packing is 6. The main difference between this square packing and hexagonal is that here layer by layer vertically arranged, whereas in hexagonal close packing, in the depressions of the first layer, second layer is present. In the depressions of the second layer, third layer is present. Hope you got my point. Yes. Next, when we talk about the packing in three-dimensional, packing of the atoms in the three-dimensional way, packing in three-dimensional ranges, simple cubic three-dimensional close packing, say it is SC. It is also known as primitive close packing. Very rare crystals are having this kind of close packing. This kind of close packing is present in polonium, a cube. This total cube is obtained by the close arrangement of various layers. Say single dimensional arrangement. So, this total layer is single dimensional. Along this y direction, if spheres are arranged, and along in z direction, if spheres are arranged, then we will get a simple cubic structure. Here the coordination number is 4 because 4 spheres are very close in the crystal. The simple cubic 3-dimensional structure is nothing but different layers of spheres. Say this is A layer and this is same A layer. So, layer by layer in XYZ coordinates. If it is prolonged like this, then we will get the simple cubic 3-dimensional crystal structure. So, it is having AAA pattern of arrangement. The second type of 3-dimensional close packing is hexagonal 3-dimensional close packing. Hexagonal 3-dimensional close packing. In this is a layer called A layer. A B layer whose spheres occupies the depressions of the first layer. Then you see here a triangular vacant space is formed. The triangular vacant space. If another layer like C is placed over it, like this, this is C, A over it B, A and B are present in one dimension and C layer is present over on the first dimension. You see A over B, B over again A, like that in one dimension spheres are arranged. If the sphere belongs to C layer, fills the tetrahedral void, that is important. First layer, second layer is in the depression of first layer, second layer in the depression of first layer, and the third layer is fills the tetrahedral void. The third layer is fills the tetrahedral void, then hexagonal 3-dimensional close packing will occur. In this tetrahedral voids are formed. These 3 spheres and this is the 4th sphere. 3 spheres in one plane and 4th sphere is in perpendicular plane. In between the 4 spheres, a vacant space like tetrahedral shape is formed. That is called, this vacant space is called tetrahedral void. So, when we talk about the pattern of arrangement ABC arrangement, pattern of arrangement is ABC. Hexagonal close packing is present in magnesium and zinc. Hexagonal close packing is present in this type of metals, and the coordination number is 12 for this close packing. Let us talk about the third type in the 3-dimensional close packing. This is known as CCP or FCC. Both are same. CCP or FCC. See, this is the one layer, first layer A. Second layer B is filling the depressions of the first layer. This is second layer. Second layer is filling the depressions of first layer, and third layer is filling the octahedral void. Here third layer is filling the tetrahedral void, whereas in cubic close packing third layer fills octahedral void. That means, see here 1, 2, 3, 4, 5 and the back side is 6. This is A layer, this is B layer. The depression is filled by B layer. First layer depression is filled by B layer. 1, 2, 3, 4, 5, 6. This is C layer. So here ABC type of arrangement occurs in CCP. In hexagonal AB type, in cubic close packing ABC type of pattern is available. When we talk about the coordination number, here 6 spheres, here when this 6 plus 6 plus 3 are compactly arranged, a octahedral void is formed like this. Octahedral void is formed 1, 2, 3, 4, 5 and back 6. In single dimension we can write 1, 2, 3, 4, 5, 6. The coordination number of octahedral void is, coordination number is 6, not 8. Coordination number of tetrahedral void here formed is 4. Coordination number of octahedral void is 6. That means 6 spheres when come close to one another, then the empty space will be like octahedral. We can also represent like this. Here one sphere, 2, 3, 4, 5 and back 6. So, in a CCP crystal formation, octahedral voids are formed. In the HCP crystal formation, tetrahedral voids are formed. And the coordination number of this HCP or CCP is 12, just like HCP. Coordination number 12 for HCP, coordination number 12 for FCC or CCP. So, still for the better understanding of the students, I will give you some slideshow on this. Observe carefully. While watching the slideshow, I will give some more explanation. Close packed structures. In 3-dimensional close packing, the spheres, this green, violet, all these are spheres. See how they are closely packed. They are packing in such a way that minimum vacant spaces, see here white. So, minimum vacant spaces are present in it. That is why closed packed structures are very difficult to understand. So, with this animation work, you could able to understand in a better way. So, close packing structures basically, for our better understanding, we have classified that in 3 stages: close packing in 1 dimension, close packing in 2 dimension, close packing in 3 dimensions. Close packing in 1 dimension, you see here sphere by sphere, sphere by sphere, they are present in a single row. So, this sphere is in contact with 2 other spheres. So, coordination number is, for this dimension is, coordination number is 2. Let us have close packed structure in 2 dimensions. This is a layer, this is another layer. Here spheres are present in 2 rows. This is another row of the same kind. So, linearly and vertically propagating in this structure, linearly like this and vertically if spheres. So, see the coordination number of this packing is 1, 2, 3, 4. 4 are very closely spaced. Pattern of arrangement is A type of arrangement. And 2-dimensional close packing, another 2-dimensional close packing is this type. The main difference between these two is, here the sphere is exactly identical with the next layer sphere like this, whereas here the first row is A and second row is B. So, B spheres are exactly in the depressions of first layer. This kind of 2-dimensional packing, AB type of packing is hexagonal 2-dimensional close packing. See the coordination number is 6 here. When we move to 3-dimensional close packing, this is the first kind of 3-dimensional close packing. Here all the layers, first row, second row, third row, fourth row, this is in 1 dimension, and this side first row, second row, third row, fourth row, second dimension, this 1, 2, 3 like this. Different 2-dimensional blocks are arranged in XYZ coordinates. This whole primitive or square packing unit cell is formed. This is known as primitive cubic close packing. Its coordination number is 4, A type. This is the hexagonal close packing. In this 3-dimensional way, it is very easy to understand. The green balls are referred to as A layer and the pink balls are referred to as B layer. See, here the T which is represented over there is a void. This is a void, is represented by T. So, how they are arranged? First layer, this is the second layer, again this is the first layer, this is the second layer. So, AB type of arrangement. Second layer is arranged in the depressions of the first layer, see here and here, and again first layer is filling the tetrahedral void. First layer is, third layer is filling the tetrahedral void in HCP. In manganese and zinc, this type of crystal is present. The packing is about 74% by space filling. Empty space is only 26%. Void space is 26%. Filling space is 74%. Coordination number is 12. Look at this. this is the hexagonal close packing. A, B, C, different colors, green, pink, violet. A, B, C type of pattern of arrangement. The second layer is in the depressions of the first layer. Second layer in the depression of first layer, and the third layer fills the octahedral void. Third layer fills the octahedral void. Then ABC type of three-dimensional structure is formed. Here the coordination number will be 12, and copper and silver, very hard metals, will have this kind of crystal structure. Both HCP and CCP are having a coordination number of 12 and packing efficiency of 74%. Let us talk about the octahedral void. See, in this octahedral void, green ball belongs to one unit cell, and pink ball belongs to 3 other unit cells. Let us talk about octahedral voids. Here, this green ball belongs to this unit cell, and this green belongs to the same unit cell. These 3 green balls belongs to the same unit cell. These 3 pink balls belongs to 3 different unit cells. See how 1, 2, 3, 4, 5, 6. These are 6 spheres. 3 are belongs to one unit cell, remaining 3 are belongs to 3 other unit cells. They are formed at this is the edge center region. Edge center region, one octahedral void is formed. So coordination number of octahedral void is how much? Coordination number of octahedral void is 6. In any unit cell, how many octahedral voids are present? Unit cell, number of octahedral voids is equal to number of atoms present in the unit cell. Suppose it is primitive unit cell, one atom per unit cell are present, so one octahedral void is present. So number of octahedral voids is equal to number of spheres. See how the tetrahedral voids are formed in the crystal. If a crystal is divided into 8 equal parts, in each equal part, one tetrahedral void is formed. What is the coordination number of this tetrahedral void? See, there are 4 green spheres, so that coordination number is 4. The tetrahedral voids is equal to double the number of atoms present in the unit cell. Suppose FCC is having 4 number of atoms, then it gives 8 tetrahedral voids in its crystal. So here in this part 1 tetrahedral void, in this part another tetrahedral void, third, fourth, and from the back side 4. Total 8 tetrahedral voids are formed. The pattern of arrangement in FCC or CCP, AB type, ABC type, AAA type, A, B, C, D, E, F type. Question is, the pattern of arrangement in FCC or CCP is, we know first layer, second layer will be in the depressions of first layer and third layer will be filling the octahedral void. So, ABC type of arrangement is present in FCC and CCP. Let us take one more question. In which 3D arrangement of close packing AA type is observed? HCP. Second option is FCC. Third option is CCP. Fourth option is simple cubic. In FCC and CC both are same. These two are having a ABC type of packing, whereas in HCP AB type of packing is present, whereas in simple cubic, that is primitive, A packing is present. So, answer is fourth option.